Yeah, hi everyone. Today I still give a presentation about the membership inference attack. This is a paper published in this year's NDSS conference, and it is from the group of Hopkins University and Duke University. And since there's some new audience here, still I will give a brief introduction about the membership inference attack. Yeah, usually there were two major concerns of the privacy in machine learning. The first one is the model itself, which can be stolen by some model extraction attacks. And while the second one is the data used to train the model. A type of this data-oriented attack, and that is focus of this paper is the membership inference attack, where adversary influence whether a specific samples belongs to the training set of a given learning model or not. Here is a model structure. Here is the structure of the membership inference attack. We have a model trained by some data. So how does the attack achieve this? The attacker wants to know whether some query data belongs to the training set. Then they will use a lot of input data to query the target model and observe the output classification with the probability vectors. And then they will use this output to do the final decisions. So state of the art of the membership inference attack are many lies on these structures. First, as we discussed at the previous slides, we now have a target model, attacker with query data, and the output classification with some probability vectors. The idea they proposed is to build some local shared models on their own data set. And then they will get the output vectors from the training set and also from the test set. Here the test set is the here the data in the test set are considered as a non-member. Then remember that the membership inference is defined as the training set of the target model. So they will label their training set output as the member, and the testing set are put as the non-member. So till now, they are able to build a binary classification as the attack model and predict the membership for the query data output vectors. However, one problem of this method or called these structures is that the attack performance depends on the transferability between the target model and the shader model. And in other words, the attack performance is related to the similarity between the distribution between the distribution from the target model and the shader model. And as a result, if the shader model are not quite similar than the target model, the attack performance will degrade. So how to solve these problems? Sorry. Before I give the solutions, I will provide some examples. For example, give some examples. Here is the experiment done by the authors. They just perform some basic membership inference attacks, and with different target model and shader models. They use F1 scores to represent the performance. Here, the F1 scores is the mean of the precision and recall. Specifically, precision represents the ratio of the real true members predict among all positive membership predictions. And the recall is the ratio of the true members predicted by an adversary among all real true members. Then the mean value of this recall and precision are the main metrics in this paper. We can say that if the adversary chooses the same models as the target model, the attack performance is relatively high, even up to 96%. But if they choose a different model, the attack performance will decrease a lot. this is the scenario that called the black box attack, since the attacker may do not have the knowledge about the architecture of the target model. So how to deal with these problems? In this paper, the author provide attack that do not use the shadow model. First, I will introduce the motivations. The motivations comes from the differential comparisons of some differential comparisons of the membership data. First, we consider that we have two data sets. Ideally, one is the training data set, that all the data in this data set are considered as the member data, and another one is the non-member data set. It can be randomly generated by the by the attackers. And then we query the model, the target model, with these two data sets and obtain a bunch of the output vectors. So intuitively, these two vector outputs should be quite different. And then second, we try to mix these two data sets just like this. We replace some data in the training data set with the non-member data. And also we replace some data in the non-member data set with the training data, or this training data is actually the member data. At this time, we still query the target model with these two data sets. We will find that these two output vectors will become more similar. That is because these two data sets are becomes more similar. Then their output will become similar. So this is the motivation of this paper, that if the output vectors queried by the two different data sets, then we measure the difference or the similarity between these two output vectors. If they becomes if the distance decrease, or these two output vectors become similar, then we can think that the movement of this data can be considered as the membership data, since they makes the two data becomes more similar. Data set becomes too similar. So here is the architecture, maybe the high-level idea of the proposed blind MI membership inference attack. Here they propose the two data sets. One is called the S-prob data set as non-member, and another is the S-prob target data set. And here we want to know that whether some data in this target data set belongs to the training data set or not. Here, the curve, here you can see that this curve dividing the space, the curve dividing the space is the boundary between the member, the right one, and the non-member. We can see that the SK non-member is located more towards the left because it consists exclusive of samples with high probability of being non-member, while here the S-prob target data sets are more or less in the middle or between the member and the non-member. Intuitively, the idea of differential comparison is to move one sample from the S-prob target model data set to the S-prob non-member data set. If the moved sample is a non-member, like the case 1, then the S-prob non-members will move farther towards the left. And here the S-prob target model will move to the right. Therefore, the distance between these two data sets are increased from the original distance d to a larger one. And in the case 2, if we move the sample, if the data we moved is a member of the training data set, like this case 2, the distance will decrease to a smaller value, since both these two data sets becomes since these two data sets have become similar, such a change in distance can be then used to infer whether the moved sample is a member or not. This is the key idea and the motivation of this paper. And then they provide some algorithms to implement this idea in details. And now I will not give the detail about the algorithm, since the algorithm is just to implement this two case comparison. I will just give some important details in their real implementation. First, a key problem comes from how to generate the non-member dataset from the target model. There were usually two general directions of non-member set generation. First is the generation of non-member. First, we can generating some new samples from or transforming the existing ones. Because the input space is usually much larger than the training set dataset, then the adversary can generate new samples, which is likely not in the training set. For example, an adversary can apply some operators on the existing samples to obtain new data. And besides, an adversary can also add some random noise like the Gaussian or salt pairs to an existing data sample to generate some non-member data set. And then after the iteratively calculating the distance, when we move a data in the probe data sets to a non-member data set, and we actually move the data only if the distance increase after the movement, then we can filter out all the member data in the probing data set. The second scenario is that the adversary do not have the free probing access to the target model, but can only obtain some output vectors of a limited data set. Then we cannot, under these scenarios, we cannot randomly generate a large of non-member data sets, but we can try to separate the probing data set into two data sets. For example, we can use some clustering algorithm like the k-means, or we can separate the data set, the target data set based on highest probability scores. For example, we choose the highest scores, for example, the highest 100 scores in the probe data set as the member and others as the non-member. Then based on this, by this means, we can roughly divide the probing data set into two data sets. And then after iteratively move data in both probe data set, we can move the data from dataset 2 to dataset 1, and of course we can also move the one from dataset 1 to dataset 2. And we only actually move the data if the distance increase, and then we can filter out the probing data set into two data set. But note that here, one major challenge here is to decide which one contains the non-member and which one contains the member, since these two data sets can look the same. Here, the author only provide the intuitions that the average prediction confidential scores of the member of the data as the membership is higher than the data of the non-members. So therefore, after we use the differential comparison attacks to obtain two pure probing data sets, then we can probe the target model to get the confidential score and sync the data set with the highest mean score values as the membership, as the data set that contains the membership. And next is the details about how to calculate the distance. Here, I think this is the most important part of the of this paper. But however, the author only gives a formula and claim that this is the best way to calculate the distance. They use a calculation called the maximum mean discrepancy of formula like this. Here the yi and yi. Here the yi belongs to the target data set, and this y belongs to the non-member data set. Here the nt and nn are the size of these two data sets, while this phi function is the feature space map. Since in this paper the author claims that they map the original output vectors into a reproducing kernel space, and however they only provide a reference here, and they do not give the reason why they map the output into such certain space rather than other latent space. And I will, at the end of this presentation, I will discuss some limitations, problems of this work, and the details about how to choose the distance will be discussed later. So far, I have introduced the motivation and some details about the membership inference attack attack models. So does everyone have some problems in this part?
Jiadong, so with the calculate the distance, so they need to know that's a training set, right?
No, you are calculate the distance of the output vectors between these two data sets.
But so you mean they need to move some data from one set to another set. These two sets are the training set, right?
Not the training set. One is the non-member set that's generated by the attackers, and one is the target data set that contains the data the attacker wants to know whether they belong to the training data set.
Yeah, so for this data set, so how can the attacker get this data set, this target data set?
This target data set, this target data set, maybe they do not need some approach to obtain this data set. They just want to know whether some data in this target data set belongs to the training data set.
But they need to move some data from the target to the non-member data set.
Yeah. Yes.
If they can't do this, why they cannot know the details of this data set? How to move this if they cannot get this target data set? How to move this item?
The attacker have this target data set. For example, here I have a data set. I have a small data set. I have a small data set of 1,000 data. I want to know whether some data in this small data set belongs to the training data set. Then this 1,000 small data set is this target data set.
Okay, yeah, that's a problem. You should introduce this clearly at the beginning. Okay. So actually, so in this target set, so it has included the training set, and also it has a lot of noise or other things. So they just want, like, so I believe they have some other paper like doing like this. They want to know if, for example, if this data set belong to me, I want to know if my data is used for training by some company.
Yes.
Yeah, they can use this method.
Yes.
Yeah, this is a scenario. You should introduce this at the early stage. Otherwise, it's very hard to understand this.
Okay.
But what's the difference of this article with that one? I remember they have another one. Is this article? They have one so that can judge if that data, personal data, is used by some company for the training.
Oh, it is this data.
Or is this article, right?
Yes.
Okay, I see. Yeah, this is a very important application scenario, so that have considered. So you should introduce this early.
Okay. Okay. I'm sorry that because I have introduced two membership inference attack before, so okay. Another time when I introduce even the same attack scenario, I will still give a comprehensive application scenario about the attack.
Yeah, I think also this application is the major selling point of the article, right?
No, they just mention this scenario in the introduction part with just one sentence.
Okay.
And this is only the one proposed scenario in their paper. They also considered other attack scenarios.
Okay.
Such like just an attacker wants to steal the data in the training data set.
Okay.
And I think the most selling point of this paper is that they do not need the shared model at all. They just use the comparison of the distance between after moving some data. So they do not need the shared model to train a classifier.
For this, Jiadong, I have another question. So I can understand the general idea, you try to separate the target data set from the non-member data set, right? Use the distance metric.
Yes.
Probably here you just use like discreted, it's not like a stochastic optimization, stochastic distribution. You have some KL or some other thing. It's more like a discrete one, right? But
yes.
General idea is the same. But my question is how complex is this algorithm? Because for this one, probably you need to try every possible data point in one of the data set, right?
Yes, yes.
I think that will be if the data set is huge, like ImageNet, that's mission impossible compared with the shadow model one. Shadow model one, whatever model you choose, you still have a way to work it out. The only issue is the accuracy is high or low.
Yes.
But this one, you try every possible data point in the data set.
Yes, they need to try to move each data in the target data set.
That's a problem. That's very complex.
Yes, in the experiment, however, in the experiment, the largest data set only contains 30,000 data. That's the largest size.
Exactly. I mean, the idea is kind of intuitive.
Yeah.
Everybody know, it's like just unsupervised learning. We do the clustering,
Yeah.
but they just use the distance between two distribution, as a metric to do that. But if you try, you enumerate and try every possible data point, that's a problem.
Yeah. Yes, but the other do not mention the complexity of the algorithm.
Yeah, I think they need to traverse all the data in order to find all the variables. So there's no point to analyze the complexity because they need to do everything.
Yes, and in this paper, they actually provide some algorithm, but the algorithm actually is quite simple. That just iteratively move each data from the targets to the non-member and calculate the difference, and then compare the difference, and finally actually move the one cause the difference decrease, just like this.
Well, I will not say it's stupid, but it's it's very complex. It's just like I think several years ago we read another paper. They try to say, okay, if I want to add noise on a picture, right? So which pixel, which section I want to add the noise on, right? So the author just try every possible pixel of that picture, of that image, right? So then determine, at which pixel you need to add the noise. right? So that's well, I will not say that's not possible, but that's too complex. It's just too complex to finish, right? So but anyway, I just reserve my concern here. It's very complex.
Yeah, probably they just want to show the idea, so they never consider this practical things, so complexity things.
Yes, and even under this scenario, that order cannot generate cannot generate the non-member data set by just dividing the provenance set into roughly into two data sets. They will then the iteration of the movement will not only the moving from the probing data set 2 to probing data set
Yeah, it
1.
will be very huge
Yeah.
number of
Yes.
huge number of iteration. Yeah.
I think it can work for a very small data set, but for big one, probably no.
Yes,
Also,
and
yeah.
Dr. Pan, I think maybe they do not want to do a large inspection of some data sets, that whether some of the data in this data set are still used for training some models. Maybe, for example, just like the scenario mentioned by Dr. Yuan, I am an author. Maybe I'm a imager. I'm a painter, and I paint some painters on the and put them on the website. But now I want to know that whether, for example, my 50 my 50 pictures are used by the Google to train some models. Then I can use the attack. I can use this attack with a proper data set of only 50, just like this.
Could you repeat the
Oh, sorry.
example again?
Yeah. Dr. Yuan has just mentioned the scenario that I am, for example, I am a painter and I paint some pictures. But however, this picture, I do not grant the permissions to Google companies that to use my pictures to train their maybe classification models. And now, based on the attack, based on this attack method, I can construct a target data set of the 50 pictures that painted by on my own, and generated some non-member data set, and use the method to query the model, for example, trained by the Google, and examine whether my pictures is still used by the Google company. And under these scenarios, the size of the target model can be controlled by the attacker or by my own, since they do not need to inspection a large data set to go through all the data. Just for example, intentionally.
Okay, I got your point here. But another question is, okay, if you use a small data set, right?
Yeah.
Let's say like 50 pictures, you want to separate that to two different data sets. One is a non-member, one is membered, right?
Right.
So is it accurate enough? Is if only 50 picture or 200 picture or probably 1,000 image? My guessing is the more images you use, the more accurate results you will get. But at the same time, the complexity will be high. You know, the complexity will increase.
Actually, in the experiment, a small data set can achieve better performance.
If you go to extreme example, right? If I only have two images, definitely I can separate them. I will tell, okay, one of them is in the target data set, one is non-member, right? But is that accurate? No, I don't think that one will be accurate.
Well,
right?
Under this scenario, then I have two pictures and all of them belongs to the province data set. I will random generate some non-member data sets.
No, I mean, if you altogether, okay, okay, if you have only one in your problem data set, you're going to randomly generate a non-member data set. Okay, then how can you tell which one is the target one, which one is non-member one?
Yeah, that's the problem.
Yeah, that's true. Yeah, I also have this concern. So even you can measure distance, but the probably this non-member one probably is used in the training set.
Exactly.
But,
So I think the trial data set cannot be too large or too small.
Yes.
It should be a medium size, like 3,000 things they're using here. If it's too large, like Dr. Yuan and I mentioned, the complexity will be super high. If it's too small, I think the accuracy is going to be a problem.
Yes. Yeah. But however, in this paper, they do not do the experiment to vary the data set size and give the accuracy variations versus the data set size. They just roughly use the training data set and the target set data set at roughly about 10,000 size, just like this.
But you know, the extreme examples is the typical things we need to consider, not only in machine learning paper, in whatever paper, right? For example, I think my advisor mentioned one thing to me when I was a PhD student. Actually, he cited that sentence from Dr. Qian Jiang from HKST. Dr. Zhang basically said, you know, if you want to analyze a network of things, you start with 3 nodes, right? 2 nodes is not network, 3 nodes is network. If you can, you know, get a very clear idea of how 3 nodes works, then you can scale it up. Then probably your scheme is going to work. That's exactly the extreme examples you need to we need to consider, right? So for this one, either very large data set or very small data set, we need to consider that. Anyway, I always have some reservation for their papers though, but I don't know.
Yes, and at the last of the slides, I will provide another maybe two problems of this paper, and not only the data size, but I will try to challenge their motivations.
Okay.
Yeah, but however, in this paper, Dr. Pan, maybe I think the most contribution of this paper is that they just give a new insight in how to do the membership inference without the shadow model to train a classifier. Maybe you can use another matrix such like the difference between the movements, something like this, to do the membership inference rather than just training a classifier, just like the previous two papers I introduced. Maybe.
Yeah, I got your point here. Yeah, but still, you know,
not quite very practical, right?
Yeah, people don't use this approach for a reason, right? For example, this one, yeah, it's purely based on the data, right? And everybody, I will not say everybody can think of that. Even people that does not know learning, right? They know the basic idea of membership attacks. They can think of that, right? So you just try to separate the two distribution actually. But the thing is, it's not that practical. So probably at a very early stage, some researchers will kill this idea. You know, will not continue because the complexity is super high. It's not affordable. So if you argue in this way, well, it really depends though. Yeah.
Yes. I think maybe their selling point is just they are the first paper that without the shared model, and the review just think this is a great improvement. If there's no questions about the architectures, I will continue to introduce some interesting experiment result and discuss some drawbacks in the attacks. In here, in this paper, they quite do extensive experiments with 8 data sets, and this 8 data set covers medical records such like the AirPax and the minutes, AirPax minutes and the text. These are the medical data set, and also some personal information such as the adult location or some purchase 50. And besides, they also do the benchmarks data. They also do the experiment on the benchmark data sets, such like the CFR 100 and the birth 20, like this. And also, yes, maybe in our work, we can also do some experiments on on this different practical data sets rather than just focus on the CFR 10, CFR 100 or the image names just like this. I think maybe this is one of the advantage of their paper. And since they have the 8 data set, they just separate the data set, and half of the data set are used to training the target model, the model that the attackers want to attack. And half of the data are used for probing, that will be used as a target, will use to construct the target data set. And also the audit will generate some non-member data set and mix these 2 data sets as different ratios to compromise the target data set. And first, the author shows the distance variations between the movement during the movement of some data. And here the bench size 20 means that they moves in each steps they moves 20 data. And here the x-axis here they move the data in from 0 to 50 to 40 iterations and show the distance variations. And we can observe from figure that this figure that the distance are actually the distance actually varies after the movement. So this result confirm that the distance variations somehow can actually indicate that some data are membership or some data are not memberships. And besides, they do the compare. They also compare their blind MI attacks with other state-of-the-art membership inference attack. And also they consider the 4 scenario. Here the blind scenario is the most strict one. And the attackers do not know the architecture of the target model and also do not know the ground truth label of the training data set. For the black blind, the author knows the ground truth label of the data set, but they do not know the architecture of the target model. For the gray blind, for the gray blind scenario, the attackers know the target model's architecture, but they do not know the ground truth of the data set. And for this gray box, or maybe this can be white box, since the attackers not only know the architecture of the target model, but also know the ground truth about the data set. And we can, from this figure, of course, we can see that the attacks are always outperformed than the other state-of-the-art attack method. And further, we give a more detailed analysis. We can see that the performance of the state-of-the-art based on shadow model is unstable, which depends on the knowledge they know for example, there are 28% decrease from the black box, from the black box to the gray box on the location data set, and also the 70% of decrease for purchase 50 and the 38% decrease for the blind 20. And however, the proposed attack method by the in this paper performs very well among all settings, because they claim that they do not use any shadow model, so that their attack method will not be influenced by the knowledge about how the knowledge of the target model and the ground truth of the labels. And also in this paper, they do quite different extensive experiments about some parameters. So for example, the iterations, some threshold, or some different non-member generation methods. But I think all these experiments are not interesting. I just to show that their proposed attacks are quite outperformer, and so I do not show all their results. I think they are not interesting. But in the papers from the Jiadong group, their attack methods are always outperform than all the state of the art attack. And somehow I'm quite doubt about this, because for example, in these tables for the gray box, that the attackers know the architecture of the target model, and they know the ground truth of the training data, and they know the ground truth of the training data set. Under these scenarios, I think the membership inference attack with the shared models, I think intuitively, the shared model can perform quite similar performance to the target model. And I think under this scenario, the state of the art attack can really, I think these attacks should outperform than the attacks proposed in this paper. But however, maybe they can do some tuning of parameters to let their proposed attack outperformance than others. I think it is quite a little bit weird. Since in the like a white box scenarios, the shadow model seems to be the most strong tools to do the membership inference, just like this. So I do not trust in the experiment result, since I'm also worked on the membership inference. So in my work, I will actually reproduce the experiment and compare it with these attacks. And in the future, maybe in the next presentation, in my next presentation, or I will send the emails to the audience about the result. About the reproduced result. So yeah, if you are interested in this result, you can also email me, and I will free to give you the results about this. And beyond the trivial experiment results, I will discuss the two important problems in this paper. The first is the motivation, and in other words, that is the foundation of their proposed attack. Their attack is based on the observation that if we replace some data in the training data set with a non-member, and the non-member, and replace some data in the non-member with the training data set, the output vectors will become more similar. Yes, this is true. But however, a more similar output vectors, it is not necessary. It is necessary, but not sufficient. Not sufficient to indicate that the distance variations is caused by a training data set movement For example, maybe a movement of a data makes these two data sets similar in the distribution, can also make the output distance, can also make the output vectors more similar. Then I think the most important part is how to determine the distance calculation formula. In other words, we need to ensure that the distance variation calculation can measure the difference caused by the membership data movement. But however, in this paper, the authors just mention they just give a distance calculation formula and claim that this makes sense. But however, they do not provide any judgment and analysis of this distance calculation method. So in their experiment, as I mentioned here, they just use the same data set and divided it into two data sets, one for probing and one for training the targets. So we can say that these two data sets are actually in the same distribution. So probably the distance variation can actually caused by the movement of some membership relationship. But in the practical attack, we cannot ensure that these two data sets are in the same distribution. And then the similarity, the distance variations of these output vectors can actually caused by many other factors rather than the membership influence, the membership reasons. So I think this is a quite big problems of their papers, And another problem is about the probe data set, how to construct the probe data set. Although in this paper, they have adjusted the member to non-member ratio to measure the different performance. We can say that the non-member to member ratios varies from 1 to 50. And however, even to the 50 non-member to one member ratios, we still have 2.5 percentage data in the probe data set as the membership. So actually, of course, by the attack method, we can filter out this 2.5 percentage membership data. But however, in the more practical scenario, maybe the probe data set contains no membership data set. Then what will happen in these scenarios? The author do not do the experiment. And if the target data set do not contain any membership data, it can still iteratively calculate the distance and do the movement. I believe that they will find some data that makes the distance become small, and then they will separate some data, and they think this data should be the membership influence. This data should be a membership of the trained data set, but it will cause a quite big problems. So yeah, these are the two big problems I think this paper need to be improvement. In this paper. So does anybody have some questions about these two problems? Maybe we can have a in-depth discuss.
Okay, so any questions?
For this one, I think I want to echo Jiadong. You know, machine learning, as we all know, fundamentally is a kind of statistical science, right? But here, actually, what they use is only one dimension knowledge of the statistics. They only use the distance between the output, and then they do a reverse way to say we try to separate the two data set or something. They only use one possible feature of that. So yeah, I really don't know, because if we can use the, the distance to perfectly do this, then why do we need a machine learning? I believe machine learning can extract more features, from statistical point of view. That's the original purpose of machine learning, right? So if you only use the distance, you can easily separate two things. Then you can do the, the judgment or something, classification or whatever. Then the machine learning model in the middle is not that useful, right? So yeah, I kind of very agree with Jiadong about this point.
Yeah, that's true. Yeah, so if this distance works, so we don't need to have this deep learning things. Every time just measure different distance, and then find the close one. Then they can be classified into the same group.
Yes, that's true. If you can admit this, then we don't need any kind of machine learning, right? Just traditional statistical distance will be good enough, right?
Yeah.
Also, machine learning typically work on the large data set and very complex model. That's the typical problem setting. If you work on medium data set, yes, definitely you can use the correlation, distance, a lot of statistical features, but that's good enough, right? So why do we need a machine learning to extract more? So yeah, it's true. This paper is really questionable. Yeah.
Yeah.
Yeah, for this part, I have some thought. Maybe we can just like this. We just generated two data sets that they do not contain any data that belongs to the training data set. And then we use the movement attack and try to calculate the distance. Since at this time, there's no membership, there's no data belongs to the training data set. Then the distance, the distance variations in some space are not characterize the membership relationship. So we should choose the distance that have no has no variations under these scenarios.
I'm kind of agree with you. I want to say the similar things. Here they basically they use the the distance to calculate things. Can we add some other features? This is just a distance, just one-dimensional statistical feature, right? So if we add another layer's statistical features, whatever second moment or whatever things, right? So probably we can get a better result than them. Right here, they just use the distance. I mean, beyond distance, is there any other things? Can we combine the distance together with that one? Probably we can do better membership for inference attack.
Yeah, and I think when we choose the matrix, I think we need to build we need to build at least some relationship that we can make sure that this matrix, the variation of this matrix is resulted from the membership relationship, not the distribution variations, but just caused by the membership variation. I think this is quite important.
Yeah, if you can quantify that, yes, potentially, definitely. I mean, even you don't do that, even we just add another dimension of statistical features, probably we can do, I mean, simple way. I mean, what you said is more, advanced approach, to add another dimension of, statistical feature. But even basic, you use a very basic one, for example, I don't know, probably correlation or whatever, right? So together with the distance, I think you can do better judgment, better attack, something like that.
Yes.
Yeah, and here I think if they use the correlation is even better than the distance. So So why they just use the distance? It's a problem.
Yeah, if you jointly use the correlation distance, probably.
Yeah.
And like I said, because it has a lot of statistical features. It's not only correlation distance. You can use the correlation distance, feature 3, feature 4, feature 5. You know, you put everything together, then I think you add one more layer or add one more thing, then you can do better attack. But I also agree with what Jiadong said. If we can add some statistical feature relate to the membership inference attack, then potentially they can improve a lot. But the problem is, can we find that kind of feature or not? Right? So
yes, that's what I am thinking recently.
but even you can do that, I still think well, that's kind of a questionable thing.
If there are two symbols that we just find some deterministic matrix.
Exactly. Also, is that if those metrics can work, again, like Dr. Yuan's question and my question, we don't need to use machine learning, right? So
yeah, maybe we can use machine learning, maybe like some generation model to try to generate some latent vectors of the latent vectors to characterize the membership relations, and use these latent vectors as the
but
matrix.
also you also need to consider the complexity issue. I mean, for their paper, I don't know why reviewer doesn't raise this issue, but if for our own paper, I believe definitely that's one targeted issue everybody is going to criticize, right? Because that's too complex. Even for attacker, we don't consider the the resources or whatever of the cost of the attacker. It's still too complex.
Yeah, that's a problem. So if we have this complexity problem, our article will definitely be rejected.
Yeah, but however, there were many drawbacks in this paper, but I think their motivations are quite surprising when I first read this paper, since we can have some, we can try to find some method to give up the shadow model. Yes, I think this is quite good insight in this membership inference attack, and yeah, I think that yeah. Anyway, this is their selling point.
Okay, so any other question? Okay, so if no questions, so we are done for today's meeting. Okay, thank you everyone.